Hello everyone. We are talking about molecular spectra, and now we want to see how the vibrational energies for molecules are quantized. So just a few additional things I want to add in the previous lecture. So this I is the moment of inertia of our rotating system. So this I can be defined as, so I is equal to m sub r times radius squared. So what is m sub r? M sub r is the reduced mass. So you can try to search the internet on what is the reduced mass, but for the sake of simplicity, we will just be giving the formula here. It is equal to m1 m2 over m1 plus m2. So this is the sort of like the effective mass of this m1 and this m2. So its moment of inertia is given by the reduced mass of the two atoms times their separation squared. Okay, so now we move on to the vibrational energy levels. So let's first start with a diagram. So we have M1 here and M2. So we know that molecules are never actually completely rigid. So we want to model this diatomic molecule so that there's a connection between atoms that are not rigid but sort of like a spring. So you have like a spring here that is responsible for the motion of this kind of molecule. So we are only take note that we are restricting only for diatomic molecules. There are also other derivations for different kinds of molecules. For triatomic molecules, there's a different vibrational energy level, but we are only interested in the diatomic molecules. So we have mass m1, mass m2, and this spring in between has a spring constant of k prime, and they are separated by a distance r. So if you would recall the solution for the quantum mechanical harmonic oscillator, wherein the potential is actually modeled as springs, you will see that the vibrational energy levels for this molecule is given by n plus 1/2 h bar omega. Now, this omega term is quite different from the omega on the quantum harmonic oscillator. So this omega term is actually equal to square root of k prime over the reduced mass. So k prime is sort of like the spring constant of the spring, the modeled spring, and mr is the reduced mass that we have discussed earlier. So let's try to see what this means. So we see another variable that quantizes this vibrational energy. So n ranges from 0, 1, 2, and so on. So if we try to solve for n equals 0, we would see that E sub n will be 1/2 h bar omega. So this is very interesting because at the ground state, you still have an energy. So this is the lowest state, but there's still energy. Interesting. So for n equals 1, we have 3/2 h bar omega. For n equals 2, we have 5/2 h bar omega. So again, we see quantum mechanical effects arising from atoms to molecules.